effective action as a function of gauge fields divided by lambda, which is some gauge parameter, was equal to some g of lambda. Or equivalently, that delta gamma of A is equal to g lambda delta lambda. Okay? Our condition was that delta 1 delta 2 of gamma was equal to delta 2 delta 1 of gamma. This is the so-called Wessumino consistency condition, which was basically the statement that delta of lambda 2 g of lambda 1 is equal to delta of lambda 1 g of lambda 2. So d by d. Sorry. That this minus this is equal to delta by delta of lambda 1 commutator lambda 2. G of thank you. Okay. We were trying to solve this consistency condition. But before we go back to that solution, let's note a trivial solution to this consistency. Firstly, note, of course, that g was a local function because it arose from some regulation business, some short distance business. Okay? So how do you get local functions that obey this condition? There is one very simple way. Suppose we choose some other local object f of A. This is local. And let g equals del by del lambda of f of A. The gauge variation of f of A. Then this condition will be trivial, because this left hand side will be del by del lambda 2 del by del lambda 1 minus del by del lambda 1 del by del lambda 2. This means gauge variation, right? Where I say del by del lambda 1, I mean change, because maybe I should call it delta lambda 2 delta lambda 1. Okay, of f of A. Okay, but that would be the same thing as the change. I'm replacing del by del lambda 2 by delta of lambda 2. This would be the change under, by definition, because commutation relations of two gauge transformations, lambda 2 lambda 1 of f of A, which would be g of lambda 2 lambda 1. Right? I mean, I've said very little. The condition that we got, this condition came from the fact that g was the variation of something. So g is the variation of something, it of course obeys the equation.
How this is trivial? This is the solution we are looking for.
No, but this is trivial if f of A is itself local. I give you any.
G has the same status as gamma, right?
What?
You want to find gamma.
But gamma is not a local function.
Oh, okay. If A, that is the
Right. So I can, for these Wessumino consistency conditions, I can give you any function fa, choose its variation, and that's a solution to these equations. So any local function fa, its variation will give you a local solution to these equations. But these are, firstly, this is trivial because it is very easy to do. I give you any function.
So this is the case when the effective action itself is local, right? Because
well,
by definition, G over there is a...
The effective action, it needn't be local, but it could be a gauge invariant piece that's non-local. The part that is not gauge invariant
does not depend on
is local.
Okay.
Okay? Now this is physically trivial because this is the situation in which you can change the definition of the effective action by adding a local counter term. The local counter term being gamma a, being Fa. And then the effective action would have no anomaly.
Yeah, this is a non-anomalous.
This is actually a non-anomaly. So we are only interested in solutions to this Westermino condition modulo addition of G with variation of a local term. Because variation of a local term is just changing the local counter term in our theory to make it the best thing possible. This is like we did in our example yesterday.
Yeah.
Example in the last class. Is this clear? The interesting solutions are those that cannot be written as variations of local counter terms, but are by themselves local. Is this clear? That's what makes finding solutions to these equations hard. Okay? And that's good because, you know, the equation itself is so constraining that we can write down effectively the most general possible solution. Okay. Now, what is the most general possible solution? We started the algebra for that yesterday, and I'm going to remind you. Suppose we were in d dimensions. D was some 2m. Okay? We looked at a structure in d plus 2 dimensions and in d plus 1 dimensions. The structure we looked at in d plus 2 dimensions was some gauge invariant polynomial which was made out of wedge products of forms. Okay? So a typical thing was like trace f to the power f to the power m, exactly, m plus 1. Okay? As you will see, we will also allow products of such forms. But this is just an example. Okay. Then we noted that every such quantity could be written as d of some Chern-Simons term, which was 2m plus 1 dimensional. Okay? So they were associated with this d plus 2 dimensional form or 2m plus 2 dimensional form. There was a corresponding 2m plus 1 dimensional form. The relationship being that d of the 2m plus 1 dimensional form was the 2m plus 2 dimensional form we started with. The original thing we started with was nice and gauge invariant. The thing that we got at the end was not gauge invariant. Because anything that is made that is an odd form cannot be written entirely in terms of field strengths, and so locally is not gauge invariant. Okay?
But only integrated over.
But had the property that integrated over space-time was gauge invariant. Because it was, because therefore we have that, yeah. Delta of omega 2m plus 1 is equal to d of some form which is 2m plus 1, let's call it g, which is a 2m form. Okay? Now, let's check the consistency of this equation with this equation. The thing we started with, okay, the thing we started with, trace f to the part m plus 1, was a gauge invariant object. Okay, so delta of this was equal to 0. So 0 was equal to delta of this. But that, by definition, is d of omega 2m plus 1. So it's delta of this. So this also has to be 0. But that's equal to d of delta of omega 2m plus 1. But that is equal to 0 because delta of omega, because this is d squared of g. and therefore is equal to 0 because d squared is 0. Okay? So if you can write f as d of something, then the gauge transformation of that something will have to be d of something else, because the original trace f to the power n plus 1 was gauge invariant. Is this clear? It's a local statement, right? So it can't have some global issues. Okay? That's why it had to have this. It had to be a Chern-Simons term, where you define Chern-Simons terms as things that are gauge invariant despite, whose integrals are gauge invariant despite them locally being, that transform like d of something. Okay? Excellent. Now you see the following. Suppose I've used the symbol G here. This was the same symbol I used at the beginning of the class for the anomaly. So suppose we define G by descent from the anomaly polynomial trace f to the power n plus 1. Okay, so this going down 2 steps in dimension is called descent. And the thing that you start with in d plus 2 dimensions is called the anomaly polynomial. Note the anomaly polynomial is just some nice gauge invariant object. You want that to be true, so that the guy in dimension d plus 1 dimensions is a Chern-Simons form. Okay? So that its variation under gauge transformations is d of some d-dimensional form, and that d-dimensional form is going to be the thing that's the G that we were interested in, the variation of our effective action. Now, why is this a good thing to do? The point is that this procedure automatically solves the Westermino conditions. Why is that? Imagine that we've got our d-dimensional manifold occurring as the boundary of some d-dimension 1 manifold. Okay, so for instance, if our to picture it, imagine a circle and a disk, but of course it's some higher dimension. Or you could imagine okay, that's probably the limit to which imagination. Maybe you could imagine a solid ball. Take a sphere and a solid ball. Okay, so the 3 manifold is the solid ball, the boundary is the sphere. That's like the circle and the disk, but you can't go too much higher. Okay, so let's look at that. Okay, so now I want the variation of the integral of G on my, let's MD. Okay, but this, now since this MD was the boundary of some MD minus 1, MD plus 1, okay, this is the same thing as delta of dg exactly on MD plus 1. Right? But dg was delta of delta omega. And therefore, this is 2 deltas. Okay, so now if we do it more seriously, suppose this G was associated with delta 1, and this was associated with delta 2. So we're doing delta 2 of delta 1. We get this, but if you do the other order, you'll get delta 1 of delta 2. So this is delta 2, delta 1. But this is delta 1, delta 2 of omega. You subtract the 2, you will get delta of 1 commutator 2. But delta of 1 commutator 2 of omega was by definition dg of 1 commutator 2. Then you do the integral over the d plus 1 dimensional manifold again, and you get g at One commutator 2. The basic point was, now we've managed to make G delta of something. More precisely, we managed to make the integral of G delta of something. G itself was not. Okay? We took the integral of G, that was the integral of dg, which was then the integral of delta omega. So, integral dg was equal to integral delta integral omega. This is the key equation. So now integral dg is delta of something. Once we got that, the Wess-Zumino condition has to work, because Wess-Zumino condition works if your anomaly is delta of something. Okay? And this something was nice and local in d+1 dimensions. But it was not local in d dimensions. Is this clear? Okay? Okay, great. Okay, now, oh, ha, ma'am. Ha. Oh, you managed. Okay, excellent. Ha. Okay, thanks. Yeah, bye. Okay. Right, so where were we? So far we worked this out for a particular example. Let's say trace f to the power m plus 1. Okay? But now suppose we were, for instance, in, let's be in 10 dimensions, because that's where we want to be. So we want to be in 10 dimensions. So one thing we could write down is trace, one thing we can write down, we don't want to write down anything that's 0. Okay? Yeah, and trace of yeah. So we're in 10 dimensions. We want to write down our anomaly polynomial, which is now in 12 dimensions. So one thing we could have written down was trace of f to the 6. Trace of odd powers of f are 0 for the usual reasons. But even powers are not. Okay, this is always, remember, f wedge, f wedge, f wedge, f wedge, f. Okay, because we want to be able to use this Chern-Simons business. And this Chern-Simons business only works for f wedge, f wedge, f wedge, f. Okay, so one thing we could have written down was this, but there's another thing we could have written down, trace f squared, trace f to the 4. Okay, now how does this work? What is the, could this also work as an anomaly polynomial? Okay, so we want to write down something such that this is d of that. Okay, but suppose, now we know that there is an omega 3 such that d omega 3 is equal to trace f squared. And we know that there is an omega 7 such that d omega 7 is equal to trace f to the 4. And we also know that df is equal to 0, at least within traces. Okay? Yeah, more seriously, it's equal to 0. And therefore, if we just do this, if we just do omega 3
wedge d omega 2.
No, yeah, sorry, omega 3 wedge trace f to the 4.
Yeah.
Or equivalently, if we did
Trace f omega 2 wedge trace f squared. Yeah.
trace f squared wedge omega 7, exactly. Trace f square wedge omega 7. Either of these would work. Okay, d of this object okay, would be equal to
Trace f square, trace f4.
trace f square, trace f square. Moreover, the variation of this is d of something, but then you can just pull the d out of the whole thing because d acting on this guy is 0. Okay? So, though in our example we had one trace of one object, you can easily just multiply traces of any objects. Those will all work. Okay? So, the most general solution to this Wetzumino condition is to write down the most general gauge invariant polynomial, always using wedge products, because you want each of those polynomials to have the property that its gauge variation is d, that it is d of a Chern-Simons form. Okay, the most general solution is just write the most general non-zero polynomial you can, keeping it gauge invariant, and that parameterizes the most general solution of these Wetzumino consistency conditions. Okay? And it's a very beautiful, now what we have done here is to show that this is a solution. There is extra work to show this is the most general solution. People have done this. Okay? So the structure then of anomalies, at least of these continuous anomalies, is extremely simple. The set of allowed possible anomalies is just written down by these gauge invariant forms in d plus 2 dimensions. Okay? So now let's take an example. I'm going to have to go in like 5 minutes, but let's take a quick example. Let's look first at the anomalies for type 2b theory. Now, so far I've just told you about the general structure of these anomalies. Okay? But if you understand this general structure, now you can do a calculation to compute the anomalies. How can you do the calculation? Well, the calculation is very simple. Suppose I tell you that the anomaly polynomial is trace f to the power 6. Okay? This by descent will give you some structure of what you get at on your right hand side, some 10-dimensional form. Now this 10-dimensional form will have terms with will have terms that are a to the 5 and higher because of the nonlinearities. But there will be terms that are like a to the 5. Is this clear? Just let me give you an example. Suppose we start with trace f squared. So we were looking at anomalies in 2 dimensions. So the anomaly polynomial is in 4 dimensions. This is going to be the example we looked at last class. Okay? So we start with trace f squared. Okay? Now the anomaly the 3-dimensional form is a dA plus 2 by 3 a cube, the usual Chern-Simons form. Okay? But we know that this is d of f. I mean, it's variation. Fine. That variation of this is variation of is d of trace lambda f. This formula we had in the last class. And so the descent relation tells you that trace f squared, the anomaly polynomial, is related to this Chern-Simons form and therefore to this g. Now this f has a term that is d mu a mu, but it also has a term that's a by j. Okay? But you know, the fact that it had the a by j was related to the fact that it was an f. Okay? So if you compute just what you can about the term here that is linear in A, You've got all the information about the anomaly polynomial. Okay? Similarly in higher dimensions, the lowest order term, because we started with um, 6 A's and higher, and we took a gauge variation at some point. That gives you terms with 5 A's and higher, because in gauge variation 1A, there are terms in which 1A becomes a lambda. Okay? So the term with the lowest number of A's on the right hand side will always be 5 A's. Okay? So now this anomaly polynomial was the variation of the effective action, but as you remember, that was also del mu of J mu. So what you want to do is to find the term on the right hand side of del mu of J mu that is fifth order in A. That is the simplest calculation you can do to completely determine the structure of the anomaly polynomial. Once you have that, you can reconstruct. There's enough information. Now what kind of diagram is that? You see, J mu is whatever a J.
Hexagon.
Exactly. But we want 5
other insertions of A.
Insertions of A. Now J is precisely the operator that would couple to A. So while actually what we want is this, you can think of it as this, where instead of putting an A here, you finally put a derivative there. Yeah, you replace the epsilon mu of that by d mu or k mu. You replace one of these epsilons by k. This diagram is the diagram you will have to compute. Okay, this diagram is the diagram you'd have to compute in order to compute this d mu j mu anomaly. Okay. Now there is one more thing that I did not tell you. Okay? And I'm not going to explain it to you in any great detail, but let me just mention it anyway. You see, I told you that I am going to take my integral dg, my integral g, and replace it by integral d of this omega. Now, there is actually an issue here. Let me explain this issue in a three-dimensional context. Okay. Suppose I am interested in my surface being a two-dimensional surface. Let's say the S2. Okay. Now, imagine that we have an S3. Okay, we've got an S3 and the equator of this S3 is an S2. Okay. You can think of this S3 as one part of the S3 as filling up the S2 ball, and the other part of it is filling up the S2 ball but compactifying infinity as well. The outside filling up the S2 ball. Okay? Or however you want to think of it. So there's an S3, there's an equator which is an S2. This is one filling of the S2, this is the other filling of the S2. Just like if we were in one lower dimension, we would have a circle which was the equator. You could fill it up in one disk or the other disk and join these two disks to make an S2. Okay, it's the three-dimensional version of that. Okay, so we've got this two-dimensional space on which we want to compute our anomaly. Let's say we had the theory we were talking about yesterday, the current algebra. Okay, and now I told you that we can get this object here. I told you we could get this object here by either taking the integral of d omega 3, by taking the integral of d omega 3 on a manifold for which this S2 was a boundary. Okay? But you see, in this example there are two manifolds which we could work. We could take this filling of the S2 or this filling of the S2. So we've got two different ways of doing it. And you could ask, do both ways of doing it give you the same answer? Okay? Now, both ways of doing it will give you the same answer if the difference between these two things is 0. Okay? Now the difference between these two things is the integral of this Chern-Simons form on the full S3. So the difference between these two ways of filling it up. Okay? The difference between the two ways of filling it up, which should both be this integral G, if everything's going to work out nicely, is the integral of this Chern-Simons form on S3. Okay, now some of you know that the integral of the Chern-Simons form on S3 is, while it's on any compact manifold, is nice, well-defined and gauge invariant under small gauge transformations. If we look at it under large gauge transformations, there's an issue. Okay? And this issue goes as follows. Let's take the special case of SU2 Chern-Simons theory. SU2 Chern-Simons theory, SU2, the group manifold of SU2 is S3. And we're looking at the gauge transformations on a base space that's also S3. And therefore, large gauge transformations are gauge transformations in which one of the S3s wraps around the other. The gauge S3 wraps around the space-time S3.
Sorry, why did they have two S3s?
Because SU2, its group manifold was S3.
Yeah.
Now a pure gauge transformation is choosing a gauge element at each point in space-time. So it's a map from space-time to the group manifold. Okay, in this case, I've chosen a especially simple example where the two manifolds are the same. It's clear that these maps are topologically classified by wrapping numbers. How many times one S3 wraps around the other? Only wrapping number 0 gives you trivial gauge transformations. Wrapping number 1 and 2 and 3 will give you non-trivial gauge. These are what I call the large gauge transformations. And it's easy to verify that the Chern-Simons form is not invariant under large gauge transformations.
But we have to include the Weissman-Witten term.
Weissman-Witten term in the bulk, or the Chern-Simons terms shift by a certain amount, by an integer, by the wrapping number of these things times a number. Now, if this Chern-Simons form is chosen with precisely such a coefficient, so that the change under this wrapping is 2 pi I times integer, then this quantity, while it's not gauge invariant, if it's used as an action inside a path integral, will generate a gauge invariant path integral. Okay? So this whole business about getting, so far what we have only worried about is keeping things covariant under small gauge transformations, doing everything. If you do things very carefully and worry also about large gauge transformations, worry about how you take this space and embed it in some higher dimensional space, and worry about potential large gauge transformations, this whole procedure runs into problems unless the coefficients of the Chern-Simons forms are integers times specified numbers. So now we've got something even better. Not only do we have that these anomaly polynomials, their structure is determined, their structure is determined up to possible integers. Okay? In particular, they cannot continuously vary. Now this is a great thing, because you see, you can ask, what calculation in quantum field theory could possibly give you an integer? Loop calculations in quantum field theory depend on a coupling constant. Coupling constants are continuous, so how can you ever get an integer? Well, there's only one calculation, namely a one loop calculation. Because a one loop calculation is a calculation that is independent of g square. It's a determinant, right? You take an effective action, which is a 1 over g square, and then you compute the one loop correction. That is the term that is independent of g square. It's down compared to leading order by g square, but since the original action was 1 over g square, this is order g to the power nothing. So in one loop you can generate integers, but in two loops and higher you cannot, because it depends on a coupling constant. That tells you that these anomaly polynomials can only be generated at one loop. This is a fantastic thing. In fact, it's the same argument for those who are tuned in to the argument that in Chern-Simons theory, shifts of the level of Chern-Simons theory can only happen at one loop. It's basically the same physics stated again. Because the shift has to be an integer for Chern-Simons theory to be well defined. Integers can only arise at one loop, because everything else depends on a coupling constant. Okay, so these anomalies, not only do we know their allowed structures, we also know that the coefficients in some basis are integers, and we know that they can be effectively computed at one loop, which means that these anomalies are not just something that can exist, they are effectively computable. So we need to do this diagram and do it only at one loop in order to compute the anomaly polynomial. Okay, I haven't given you this argument very carefully, but you get the structure. To do it a bit carefully requires a little work, but you get the structure of the argument. Okay, so now we're in business, because general calculations in a quantum field theory you can't do, but one loop calculations we can do. So all you have to do is to compute this one loop 6 photon scattering amplitude, replace one of the a mu's by k mu. Either it's 0 or it's not. If it's not 0, can you remove it by a local counter term? The part that cannot be removed by a local counter term, the part that cannot be removed by a local counter term is the thing which you use to reconstruct the anomaly polynomial. Is this clear? Okay, excellent. So now I will. I told you only one loop graphs contribute. So suppose we were doing gauge theory. We were doing gauge theory coupled to matter. That's gauge theory coupled to a fermion. In a one loop a fermion, only this amplitude exists in the gauge theory. It's minimally coupled fermion gives you a gauge boson. Okay, so this amplitude here would be obtained by taking the following diagram. All these propagator lines here would be the fermion, there would be the gauge boson. You compute this and you get the answer. You see from this example that not only is the answer computable, it effectively depends only on the matter content of the theory. The matter content, its representation content. Okay, I tell you the matter content and the representation content, and from that, somebody has computed the contribution of that thing to the anomaly polynomial. Okay, if there was a boson, actually bosons don't easily contribute to anomalies. Scalars don't easily contribute to anomalies, don't contribute to anomalies. But if there was a boson, you might worry about the potential of having such guys, but those are the extra atoms. You just take the guy with the lowest number of A's, because that has the information anyway. Okay, but anyway, let's imagine that we've got some fun. Okay, so now you see that this is all extremely computable. It's the kind of thing that somebody will compute and put in a table, and has been done. Okay, so now let me tell you about a type 2b theory. in type 2b theory, the chiral fields. You know, if you have a theory that does not, that if you've got matter that is not chiral, that typically does not contribute to anomalies. The reason, one way of imagining this is the following. Any field that can be, any theory which can be regulated by a Pauli-Vilas regulator without violating any of the invariances of the theory, this is a demonstration of a regulation scheme that preserves the gauge invariance. Now, a Pauli-Vilas regulator needs to couple things of different chiralities. So, if you've got, for everything with one chirality, you've got something with the other chirality. You typically do not have anomalies. There's some exceptions, but typically that happens. So suppose we were looking at 2B theory, type 2B theory. The things that contribute to the anomalies are the spinner, the Rarita-Schwinger spinner, and the thing that is also chiral, namely the 5-form gauge field. Because the 5-form gauge field is self-dual. It doesn't have the anti-self-dual part. In the self-dual gauge field can be thought of, for instance, as coming from, you know, the reason that it was self-dual rather than anti-self-dual is that it was made up of completely chiral spinners in the psi gamma psi decomposition. So it's as chiral as the spinner that created it. So the things that contribute in running in this loop to the anomalies are this, and the f, mu, nu, alpha, beta, gamma. Okay? And people have just computed the contribution to each of these, from each of these, and have written it down. So I'm just going to write down some formulas for you. The guy from the spinner, which Pulchinski calls I8, is this. The anomaly polynomial is minus trace f to the 6 by 1440 plus trace f to the 4 trace r squared, okay, by 2304 and it just goes on. If you guys have if you guys have Pulchinski, look at 12.2.11. The point is that there are trace f to the 6. There's a term which is like trace f squared, r squared, and so on. Now, one thing I should there's some polynomial. One thing I should tell you is what's this r? You see, so far I've told you about anomalies in gauge transformations. But you can also look at gravitational anomalies. So what's a gravitational anomaly? One way of thinking of it is as follows. One way of thinking of gravity is by looking at the Vierbein formalism. At each point in space-time you specify a Vierbein. Okay? And you set up everything so that the Vierbein, the choice of Vierbein doesn't matter. Okay? The transformation of, you know, the spin connection transforms like a field strength for the SOD transformation that rotates these Vierbeins around. Okay? Think of gravity in that language. If you think of it in that language, gravity becomes basically identical to an SOD dimension, an SOD gauge theory. And R becomes the field strength corresponding to that object. Okay? So R, you might say, has 4 indices. Well, every self-respecting field strength has 4 indices. It's F mu nu, AB. Just happens to be that in the case of gravity, AB are also space-time indices, but you can make it explicit that they're not by using the Vierbein to convert them into local indices. So it's just an SOD field strength. Okay? So from that point of view, R is just like any other field strength. And this kind of thing will contribute to a mixed anomaly. An anomaly that mixes for del dot f of this theory will have a term which is f cube times r square. for instance, or f, right? Okay? So anything that you can write down involving traces of even powers of f's or traces of even powers of r's can appear. So you can have an f to the 6, you can have f squared, f to the 4. You can have f4, r squared. You can have r to the 4, f squared. You can have trace f squared cube. And just so on. Anything you can write down could appear. And in general, they all appear. They all appear with very particular integers. Okay? They all have to be integers because when you multiply them by the right integers, you have to get integers. Okay, there's some integrality properties here. But okay, you get some god-awfulness. Okay, then you do it for the Rarita Schwinger. And you get some other god-awfulness. Then you do it for a, mu, nu, rho, alpha, and you get some other god-awfulness. But when you sum them up for type 2B theory, you get 0. Okay, so type 2B theory is an example of a theory that is not anomalous. Okay, and that's totally great. That's totally great because, okay, we wanted a theory that would make sense. String theory told us we should get theory that makes sense, and it does. So we're very happy. Okay, the situation is more interesting with type 1 and the heterotic theory, where we don't just get 0. Okay, we don't just get 0. So the equation for that is 0 is that if you minus 2 times I8 minus because the spinors, if you remember, are antichiral rather than chiral. Okay, plus 2 times I56. 56 is the Rarita Schwinger. Plus I self-dual is equal to 0. Okay, and this is a miraculous identity that happens to be true. Okay, things will get more interesting when we look at the type 1 and heterotic theories. We won't automatically get 0, but we'll understand why that's not a problem. Okay, I better run.